Hi, this is Andrew Livingston. This is the third in our series of summary lectures for CTR08108, Civil Engineering Principles and Materials 2. So let's have a look. Now last week we left you with a tutorial. This is the tutorial here. A solid copper circular rod with diameter 40 millimeters and length of 800 mil. Parsons ratio can be found in table 1. Copper 0.33. And the Young's modulus can be found from there's a link there, there's an extract from it there. Calculate the force required to reduce the cross-sectional area by 5 millimeters squared. Now, rather than going through the answers just now, what I'll do is I'll just show you the answers in summary, and they are on the middle page for you to have a look at in your own time. So the force required to reduce that by 5 millimeters squared would be 887 kilonewtons. Okay, right, for just now though, let's go to today's lecture. That's not the correct lecture. Where is the correct lecture? Stop that. From beginning. There we are. This is the correct lecture. I knew we had it somewhere. Right, we'll be looking at the shear load displacement and the stress-strain relationship within that shear load displacement. Then it's the mass, density, and weight, and plus our obligatory exercises. Notes from week 1 or the first lecture, and notes from the second lecture. You can pause the video, go back and have a look at the notes if you've not already got them, but I'm sure you already have. We'll be drawing upon these equations today quite heavily, so please take your time, pause the recording and go back and check things. Okay. If we look at a very small component within a piece of material subjected to loads, last 2 weeks we were looking at the axial loading. So if you pull it, as it elongates, the cross-sectional area would then reduce on the perpendicular planes. On today though, we'll be looking at it not as an axial load or a compressive load, but in fact a shear load. So as we apply a force going along that surface, we get an equal and opposite at the bottom from the top. So shear stress are denoted by the letter tau. Tau xy is the direction, equal and opposite going the other way. And then if we were to go in the vertical direction, it would be tau xy. Hope I said that correct the first time, but we'll carry on anyway. I'm sure you know what I mean. So, the ratio between shear stress and shear strain is denoted by the shear modulus. This is not the same as Young's modulus, and in fact we will touch on that at the very end. And so the equation is G equals tau over gamma. Right, what is gamma? Gamma is the angle between the vertical and that displacement. And then delta is that displacement here. If you can see my mouse, yes you can, my mouse is very visible, perfect. So that shear load displacement relationship, T is that force, and you'll recognize this from before, K over L delta. Just for your memory, this is the equation we had before, F being the force on a tensile rod. Well, same equation, but it's T to represent that shear force. So we can rewrite that equation. We have this equation here. So what do we have? Tau Tau is T over area, and area is going to be BH, breadth and height, and LB, this is the length here. It is important that we acknowledge that that's length, that's height, and that's breadth. We will go over that in subsequent weeks. So I've rewritten this equation in this format here, T over A and T over tau. It's very similar to what I'd done the last 2 weeks when I wrote the equations out, where you could use stress equals force over area, tau equals T over area, same idea. Now let's have a look at this gamma, this angle here. If we look at this relationship here, we have delta divided by L, so that delta divided by L equals tan gamma divided by 1. Now, we can simplify that down, and we can just refer to it as delta is approximately equal to gamma L. And we find that is a very good fit. So we're going to use that going forward, or we do use that going forward. And again, just to show that equation, you've kind of seen this before, where we've got delta over L and delta over strain. That's just gamma for that angle for us when it comes to shear. Okay. So let's just highlight this equation here, and we've got that, and we can represent that as T, K over L delta, which we can rewrite as GA is K, so that becomes GA over L delta. So this point is good to just take 2 seconds and have a look at the shear stiffness of a panel as a function of the material properties G, shear modulus, and the panel geometry, which is area, and area being the height multiplied by the breadth in this scenario, all divided by the length. That's your panel geometry. Okay then, so we have from our previous equations last week, notes 3.9 equation, which is this one here. So what we have here, we can denote that as strain X equals 1 over E, stress, take away Parsons ratio, stress Y. So we have that, and if it's in the opposite direction, we just change the notation accordingly. Perfect. And we also have that. Now, for isotropic materials, now the definition of isotropic materials is the physical properties don't change in relationship to the direction of the force within the material. So i.e. it's the same in any direction. So steel and concrete would be referring to in this scenario, or any metallic object. That's isotropic material. That's something you want to remember what that means. It means it's the same in any direction, or there's a better worded example here. From this equation here, the only 2 independent parameters. Hence, if we have any 2 of the 3 properties, we can determine the others from that. Okay then, mechanical properties seen so far. We've got the modulus of elasticity, shear modulus, so that's E, G, and V. Other important non-mechanical properties are density, and that's rho. And rho, or density, is a unit of kilograms over cubic meters. In many structures, the dead weight of material is of structural significance, contributes to the total permanent load to be supported by the structure. So if you use a heavier material, that heavy material has to support its own weight before it can support additional weight applied onto it by things like you and I walking on top of the floor, or any furniture or any equipment we have in the room, or wind loads, snow loads, so forth. So how do we calculate dead load? The dead weight, or dead weight load, is in newtons. So newtons equals the mass, which is kilograms, times the gravitational acceleration, meters over seconds squared. Let's take gravity as approximately 9.81 meters per second squared. So the mass equals density times the volume. Nice and simple. And then we've got force equals rho Vg. That'll be newtons. And density is kilograms divided by meters cubed, multiplied by the volume, which is the meters cubed, multiplied by gravity, which is meters over second squared. Right, let's jump straight into the exercises then. Okay, so these are the notes that I've got for today's lecture. And you may see something down here, volume of a sphere. We've not covered that yet, we're about to just now, but all the rest we have covered. So this is our exercise. A 10mm thick steel plate has been fixed on its left side, whilst a sphere of radius 0.816 meters has been hanged to the right side of the plate by considering the following data. H and L, the height and the length, are 1.5 meters, so it's a rectangular object. The radius, as stated before, 0.816 meters, that's of the sphere. The breadth of the plate is 10 millimeters. The G, shear modulus, is 8070 newtons per millimeter square. And then the density of the material used in the sphere is 7,800 kilograms per cube. Compute the vertical displacement delta at the top right corner of the plate. So, before we can compute the delta at the top right hand corner of the plate here, i.e. the shear displacement, we need to think about, well, what is the volume in this sphere? Now, you either know what the volume of a sphere is off the top of your head, which is probably a good thing to start with, if you can just remember. There's the equation there, 4/3 multiplied by pi r cubed. Now, if you can't remember that, and you're asked for that, then this is how you can calculate it. There's the equation we're going to get to. So we've got the y and the x-axis, and we've got the radius at any point in that sphere. So we know the volume of this. This is the volume equation for the sphere. We've got, using calculus, it's A to B, area x dx. So, let's have a look at AX. What is the radius of, the area of a circle? And that's just pi r squared, pi radius squared. So, and that for us, radius is going to be y, or y here, or y there, y r squared. So we want to take y out. So we know the radius of the circle is r squared equals x squared plus y squared. We can transpose that, get the y out, and then get what y is from that. It's plus or minus square root of r squared take away x squared. So we can pop that in over here into this equation, get this, simplify it down, and we've got this. Now we can transpose that ax in up here to get this. Now, obviously pi is just a number, so we can put pi outside of the calculus, simplifies it down again, and then we can then extract that out and get r squared x, take away 1/3 x cubed for r there and minus r. Again, we can extract that out further yet again. We take that x to be r, so we've got r squared r. And again, we make that as r. Same thing, we're going to do that as we go along. We can then simplify that down here as r cubed. Take away 1/3 r cubed. Take away all of this. Extract it down again. And again, simplification. Until we eventually get to the equation that we had at the very start. Or, here we go, when we extract that out. Excellent. So that's just a proof of where that equation comes from. My suggestion would be try and remember it. That would be good to go. Right, so getting back to this then. We want the delta, so we'll put delta here. We know that delta is going to be an equation of gamma L. So I'll write that there. We have L, but we don't have the gamma yet. So we're going to write down gamma down here. And gamma is an equation of tau over G. Tau, which is the shear stress, over the shear modulus. Do we have G? Yes, we have G, but we don't have tau. So tau, we're going to bring tau down here. And then tau is an equation of force over area, which is shear stress equals force over area. We want the force. We actually have the area because we've got breadth. Breadth is 10 mil. Height is 1 meter 500. So we can take F. We don't have F though, do we? No, we do not have F. Do we have F? No, we don't have F yet. So let's work out what F is. We'll bring F down here. F is going to be the mass times the gravity. Now, that would be mass times gravity. What would be gravity? Let's have a look. So that would then be mass is essentially rho times volume. Rho is the density times the volume of material. We know what rho is. Yes, we do. Rho is the density. And the volume of material, we don't have that yet, but we can easily calculate the volume. And G is the gravity. We'll use 9.81 as our gravity. It's a good assumption. So our volume is essentially 4 over 3 times pi r cubed. So we can easily get that. There's our volume there, 2.2759 cubic meters of volume. And from that volume, we can then get our force, which is 174.149 kilonewtons. Quite a force. And from that, we get our shear stress, 11.61 newtons per millimeter square. That's an amount. And then again, we've got our angle, angle in radians. And we bring that up. And then we get our displacement, our delta. Our delta would be 2.158 millimeters. Now, is that the only way that we could have got the answer? Let's have a think about it. Let's have a look. So we want delta. Do we have the force? Well, we can calculate the force quite easily. Do we have L? Yes, we had L. We had G. Yes, we had G. And area, we could have calculated breadth times height. So therefore, we could have used this simple equation here. And just put FL over GA and got our delta. Excellent. Right, please take your time, go over that again, and then try this additional tutorial question. Question number 2. You have a 10mm thick steel plate has been fixed to the left-hand side. Funny that. H is 1.5, but this time L is going to be 2 meters. Now, at the moment, we are telling you what L and H are, right? But next week, we'll discuss how to identify what L and H are, depending upon the direction of the forces. So this is shear. This is L. This is H. Okay, so L is 2 meters, H is 1.5, the breadth is 10 mil, and the shear modulus is the same as before, 8070 newtons per millimeter square. On the right hand side, there's a concrete ballast is placed. Concrete ballast. Calculate the dimensions of the concrete ballast that will give a maximum vertical displacement of delta being 5 millimeters at the top right hand corner of the plate. Exclude any elongation of the rod connecting the plate to the ballast. So exclude any elongation there. I'm only looking for the delta happening by shear of the plate. Another assumption would be BH, BB, and BL all equal each other. So it's going to be a cube. A cube. Give it a go, show all your workings, and then email it to myself, and submit it on to the portal which I will provide. Excellent on Moodle. Right, if I just go back here, so give that a shot, and then again submit it onto the Moodle page on the portal for this week, and or email it to myself as well, and I will give you written or verbal feedback on that in the following face-to-face lecture. So that concludes today. Thank you very much. Do have a look at all the additional material that I've been giving you on Moodle as well. There's more to what's on Moodle than just what's in the lecture. So please have a look at all the additional material that will be giving you week after week. Right, thank you very much.